All set.
Okay. All righty. Well, then let's go ahead and get started. So, hi, everybody. Today, Ola is going to talk to us about modeling joint speed wind distributions and wind farms using copulas. Ola is a PhD student at Clarkson University, and he's been working with us on the EXA SGD team for the past 7 weeks or so, and he's going to be presenting his work from his summer internship. So, Ola, please go ahead and take it away.
Yeah, thank you so much, Matt. Hi, everyone. Again, my name is Ola, and I'm a third year PhD student at Clarkson University in New York. So today I'll be talking about a project I've been working on, modeling joint wind speed distribution in wind farms using Copulas. I'd like to thank my mentors, Dr. Matt, Dr. Jonathan, and Dr. Ignace. All right, let's get started. So a brief description of the site, the grade we used, and so it's active 200 grade, and it contains 200 buses with 49 total generators. In particular, we have 6 wind generators. The total generating power over there is 3,602 megawatts, and the total wind capacity on a grid is 699 megawatts. So on this grid, it's over central Illinois. There are 4 locations, each containing 2 wind plants, and they are the spots in red on the picture over here. Okay, now move on to the data sets. So since we're trying to model wind speed, we have to get those wind speed from the wind integration toolkit. There are like various large data there. Data sets with like 2 terabytes, 50 terabytes, and 0.5 petabytes. Overall, it's taking over a 2x2 grid with 20-meter vertical resolution. And we pick like 5 minutes time resolution for pressure, wind speed, direction, humidity, temperature, and density. Our interest in particular is the wind speed. And to be able to filter this wind speed from this data set, we use a local tool called power scenarios. Essentially, power scenarios, the way it works is the user supply a wind farm locations, and by like supplying the latitude and longitude, nameplate capacity and minimum values for the capacity factors. And then winds, power scenarios select the closest techno-economic wind sites, meeting these minimum capacity factors and nameplate capacity. And since this is an historical data, we get the historical data over a period of 7 years and download it and store it in a CSV file. Next up, we go to the motivation of this project. So consider 2 wind farm, one on the right and one on the left. It's possible to plot the histogram of the wind speed over the period of 7 years. And yeah, we could see the distribution in this picture. From this histogram, we could do some parameter fitting and try to fit a distribution that best fits this um, wind speed data. When I do that, one of the best distribution that fits this data is the Weibull distribution. We can get the parameters, the shape, the location, and the scale. And now from this distribution, we can sample. So I can sample like any time and over any number of elements. And so when I sample, we can have something like this, which is a pretty, good sampling from what we have here. However, the question comes, the question that we have is, does this sample, does it represent the correlation between the wind farms? So if I have wind farm A and wind farm B, highly likely is that if the wind is high at wind farm A and wind farm A is close to wind farm B, there's a chance that the wind speed will also be high in wind farm B. But from this sampling, we know we would later see that sometimes without using copulas, this sampling technique does not account for the correlation between the two wind farms. So over here, okay, awesome. So over here we have the historical data between two wind farm, and then on the right here we can see how Copulas was able to, like, in the center you see that Copulas was able to like predict the correlation between those two wind farms as compared to without using Copulas, which I'll show you in a bit. So the next slide here, this is the actual historical data. Um, on the top here is wind farm 65. On the right here is the wind farm 104. And in between them is just the joint distribution of the correlation between those two wind farms. Now, if I try to just run some parameter fitting for each of them independently, this is what I get. This is not like too bad, but one thing we do not see is we do not see the pattern of the correlation between them. The joint distribution doesn't really quite align. Whereas when I use Copulas, we can see that Copulas is able to like predict the correlation between these two wind farms more closely than without using it. So next up, we just go to some theory of copulas. So essentially, a d-dimensional copula is simply a cumulative distribution function such that the marginals are uniform. And there's an important theorem which helps us um, guarantee whether or not the existence of copula exists. So it says here that is the scalar theorem, and it says that if you consider a d-dimensional cumulative distribution function f with respective marginals f1 to fd, then we are sure that there exists a copula C, a coupling function, such that the CDF of each of the random variables is simply a function of the coupling function and the individual marginals. And in particular, if this was a good distribution are independent, this coupling function is simply just the product of these marginals. Now, the idea behind how we're going to apply this is we want to build a d-dimensional distribution for wind speed such that it accounts for the correlation and covariance between these multiple wind farms on our site. To be able to do this, on the next slide, okay, so to be able to do this, we simply approximate the interdependence between these wind farms using our historical data. And then we employ the inferred distribution parameters from each wind farm to build the multivariate couplers. Now, a little bit more about this idea is the ability to be able to move from one distribution to a uniform distribution. So there's a concept of probability integral transform, and simply it states that it guarantees that from whatever distribution I am, I can move to another distribution, which is the uniform distribution. So over here, the CDFs are used to transform back and forth from uniformly distributed samples to samples with other distribution. However, there is the criteria that the distribution you're moving from or moving to should be continuous. So I could move from normal distribution to uniform, you can move from beta to distribution and whatnot, but you just have to be continuous. How we apply this is to build the coupulars. Firstly, we compute the covariance among the 6 or pairs of wind farms which we've got. After getting the covariance, then we sample a Gaussian distribution using this covariance matrix. Nextly, we transform the new Gaussian distribution, which is continuous, to uniform samples. And then from these uniform samples, we can go back to whatever distribution of interest. In our case, it's the Weibull distribution. More on this is on the next slide. So here's the algorithm we use or the process we went through to actually build this multivariate distribution. So firstly, we went to the step of data preparation. This involved collecting and preprocessing wind speed data from multiple wind farms. And we did this using power scenarios by modifying power scenarios a little bit. And the next step was to do distribution fitting for the marginal distributions. So each wind farm had like data for 7 years. And then we fit a distribution. In our case, it's the Weibull distribution to the individual farm. And next up, we compute the covariance matrix among this wind farm. And this is the covariance matrix is important because we supply it to our Gaussian distribution to get sampling from a Gaussian distribution. And next step, we transform the Gaussian distribution back to uniform variables. And lastly, we convert back from the uniform variables to our Weibull distribution using the parameters we got from step 2. And we use this multivariate distribution to make informed decisions. So here's what our result look like. So if I pick three wind farms in particular on the site, the actual historical data, this is just showing the joint distribution, i.e. the correlation and covariance between three wind farms. Now, if I try to like fit each wind farm independently and I plot it here, you would see that on this graph we do not see the correlation structure which exists in the actual historic wind farm. Whereas if we use the Copulas way of doing it, the Copulas is able to predict closely to the actual historic data patterns. Um, in conclusion, one of the important things we notice is the precise dependency modeling. In our case, Copulas captures intricate wind speed interdependencies in diverse wind farm settings. Also, we had adaptable approach. So starting with a Weibull distribution and integrating Gaussian Copula, our method flexibly fits various wind farm scenarios. We also got like strategic insights. So our techniques enhances renewable energy decision making by providing some insights into how we could see the correlations. And then future prospects is so while the Gaussian couplers was able to perform well for a particular wind farm, there's a possibility of exploring alternative couplers which may be able to like explain some complex dependencies in whatever wind site we're working on. And so one other thing which is like a future works is when I was working on this, there was like some module online that could like model couplers like just with some single line of code. However, it only supports beta, gamma, and Gaussian distribution. So essentially, I had to like code up the Weibull distribution parts locally. So one thing I intend to do like next semester I would be like trying to push this code I got during this internship to the open source and try to like make it available for others to use. Um, yeah, and these are my references. I think that'll be all for my presentation. Thank you so much for listening.